Hi, in this video, we will learn the difference between the analytical integration versus the numerical integration. In this study, we will focus to solve the engineering problem by using the analytical method, such as the analytical differentiation and also the analytical integration. On the other hand, numerical method is out of the scope. Numerical methods such as the numerical integration and also the numerical differentiation will be covered in more advanced mathematics class. In this stage, you should know how to differentiate between the numerical method and also the analytical method. Normally, numerical method is used for discrete data. For example, if you have displacement versus the time, and you have the corresponding data. So if you want to differentiate it, you can use the numerical method. On the other hand, if you have continuous data, where you have the function x equal to in the function of time, then we can apply the analytical method for the continuous data. It's important for us to know when to use numerical method or when to use the analytical method. Make sure you know how to differentiate them and don't mix the usage between them. These are some common symbols when you perform differentiation or integration. Can you differentiate which symbol is used for the analytical method and which symbol is used for the numerical method? In simple, the symbol in red color are the symbols used when we perform the analytical method, and the symbol in blue color are the symbols that we use when we perform the numerical method. For the analytical differentiation, these are the common symbols that we use. For example, you differentiate some function in f with respect to x. So we use the symbol d over dx. So you can perform the numerical differentiation by using this symbol where you take the delta f with respect to delta x. You will obtain exact solution if you perform the analytical method, and you will obtain some approximation when you perform the numerical method. For example, if you have a continuous function f equal to sine x and you want to differentiate it, so df with respect to dx, you should obtain cos x. And the solution for the cos x is written in the equal symbol. So this means that this solution is exact. In other words, it means that this solution is 100% accurate with no error. So if you plot the graph for the sine x, you should obtain this graph. However, if the data is given in discrete format in a table, where you only have some discrete data instead of continuous data. So in this case, we need to apply the numerical method. So when you apply the numerical method, in this case, we are saying that we are approximating the df over dx by using the delta f over delta x. So in this case, the solution that you obtain is an approximation. Therefore, numerical method comes with approximation error. On the other hand, if you want to perform the integration on the continuous data, so let's take the integration of the fx function, where your fx function is a sine x. If we let the upper limit x to be 2 pi, it means that we are going to integrate from 0 here to 2 pi. So substitute the sine x to the f function and then perform the integration of sine x, you should obtain negative cos x. Substitute the upper limit and lower limit inside and take the subtraction. Then you should obtain the answer to be 0. This is known as the analytical integration. And you should know that performing the integration is to find the area under the curve. So for this case, you can see that the area here and the area here are the same, but one is positive, another one is negative. That's why when you take the positive and negative area, you obtain 0 area in total. On the other hand, this equation can be written in this format, where you can see the summation of the f function multiplied with the delta x. In fact, the fx is the height, where the delta x is the width. So you're actually computing the area of a rectangular bar. Imagine that we zoom out the sine function, and then you want to integrate from 0 to 2 pi. Similarly, you are looking for the area under the curve. So now you represent this area by using the rectangular bar here. So you can see that when n approximates to infinity means that you want to put infinity bar inside this curve. And therefore, by doing this, you should obtain the width of this bar is very small, approximate to 0. Where you can see it's approximate a line. So if you continue, a lot of bar under the curve, right? So by take the summation of all of these bar, then you can compute the total area, and this total area is equal to the integration here. However, in actual scenario, it's impossible for us to compute the area by using infinity bar. So n approximate to infinity is not practical. Therefore, in practical, we use some finite number to represent for the n bar. You can see that this part is similar to this function where you have the area for a rectangular bar. X is the height, while the delta x is the width. So in this case, let's say your n is equal to 2, means that you are using 2 bar to approximate the area under the curve. Where you can see that if you only use 2 bar, so in this case, your delta x will be pi. By doing this, you are actually performing the numerical integration. You can see that the black regions are the error due to the numerical method. This error is known as the truncation error. One way to reduce the truncation error is by increasing the number of bar, where you can see when you increase the number of bar to represent the area, the error can be reduced. And by doing this, you can see the width will become smaller. So the width is known as the step size. So it means that by reducing the step size, we can reduce the truncation error. This is for your extra information, and you will learn it more in the numerical class later. Let's discuss more examples for the numerical and analytical method. In this case, we have the fx function equal to x sine x squared plus 1. When you plot it, you should obtain the blue curve. Your task is to find the slope at x equal to negative 0.5. So, what is the slope? And you should know that the slope can be represented by f prime negative 0.5, which is equal to df over dx when the x is equal to negative 0.5. You should be able to identify that this is known as the analytical differentiation. So we take the df, where your f function is substituted inside, divided by dx. Differentiate a constant 1 here, directly you obtain 0. Differentiate a product of two functions, we constant the first function x, then we differentiate the sine x squared. You should obtain cos x squared, and since the function inside is in x squared, so you need to continue to differentiate it with respect to x. So in this case, you obtain 2x. And then you continue to add with the sine x squared function and differentiate x. So you should obtain this. Once you obtain the dy over dx function, then you can continue to substitute the corresponding x. So in this case, our x is negative 0.5 and you want to find the slope at this point. So once you substitute inside, substitute all the x to be negative 0.5 here, compute it, then you should obtain the final answer. Bear in your mind, analytical differentiation gives exact solution, which means it has 0% of error. How can we solve the same problem, which is to find the slope at x equal to negative 0.5? But in this case, we are using the numerical differentiation. To find the actual slope here, if you know the delta f and delta x here, then by using this formula, you can find the differentiation. If you examine this formula closely, you will find that the limit for the delta x is approximate to 0. This means that the 2 points to compute the slope must be very close enough where your delta x here is very small, which is approximate to 0. So this limit is actually impractical in the actual situation, because in actual we can't get the delta x equal to 0. For example, in this case, the smallest delta x that you can obtain is by using these 2 points, where the delta x, which is the step size, is equal to 1 in this case. So by using this, we can approximate the slope by taking delta f divided by delta x. This can be computed easily from the information given by these 2 points. For example, delta f here can be computed by the height at point 2, which is this, and then minus with the height at point 1, which is this. And you can continue to divide with the delta x, where the delta x is equal to 1 or is equal to x2 minus with the x1. So there is a typo here. This one should follow this. It should be x minus. By doing this, you are actually performing the numerical differentiation, where the height at point 2 can be computed by substitute the x equal to 0 inside this function to give you f0, which is this, minus with h1. h1 is the height at point 1, where you can substitute the x equal to negative 1 inside this function to compute it. So divided by, at the bottom, the delta x is equal to 1, therefore divided by 1 you still remain. So by computing this, you should obtain the slope to be 0.8415. Compared to the actual slope result, which is equal to 0.7219, the approximation slope by using the numerical method here has some error, which is equal to 15%. This percentage can be computed by taking the actual solution minus with the approximate solution divided by the actual solution multiplied with 100%. Then you should get around 15% error. To reduce this error, we can consider to reduce the step size. For example, if you repeat the same procedure by reducing the delta x equal to 0.02, then you should obtain the answer equal to 0.7319. Compared to the actual slope, then you find that the error is reduced to much lower value, which is 1.4% in this case. So we can say that the accuracy of the numerical method can be increased by reducing the delta x, which is the step size. In summary, analytical solution gives exact solution or the true solution, which is 100% correct with no error. On the other hand, you obtain approximate solution from the numerical method, which has error. So now you should be able to differentiate the analytical differentiation and also the numerical differentiation. If we want to obtain an accurate solution with no error, then we will go for analytical method. instead of the numerical method, because numerical method is less accurate due to the error. However, in some cases, numerical method is more favorable than the analytical method. For example, if you have a measurement data that is obtained from the sensor, then you should obtain the data in discrete format like this. So in this case, we cannot apply the analytical method to solve the problem. So we have to use the numerical method, where you can see that the numerical method can be applied to the discrete data or the continuous data. In some cases, even though you have a continuous function, however, this continuous function is too complicated and cannot be solved by using the analytical method. For example, in this case, you are going to differentiate this function, however, is too complicated to be solved. So in this case, we can easily solve the problem by using the numerical differentiation. For example, let's say you want to find the derivative f prime at 0.5. In this method, you need to define the step size. Let's assume the delta x is equal to 1. So in this case, your x2 is equal to 1, and then your x1 will be equal to 0. So you can substitute x1 and x2 inside the original function fx here to obtain f1 and f0. Then this is your f1 and this is your f0. Substitute inside this formula, then you compute the delta f over delta x. By doing this, you can approximate the f prime function approximate to this answer. Not only that, the numerical method can be used to solve some complicated function like this, which cannot be solved by using the analytical method. Numerical method can provide a faster computation because it involves simple operations such as substitution, summation, subtraction, multiply, and divide, instead of performing derivative and integration, which is more computational expensive. We have discussed the analytical and numerical differentiation. Let's continue to discuss the difference between analytical integration and numerical integration. We know that the definite integral is integral with limit that can be represented by this formula. In simple, integrate any arbitrary function like this with respect to the x-axis from the lower limit a to the upper limit b, give you the area under the curve. If we can use this formula to find the area, then this is known as analytical integration. And the solution of area under the curve here that you find by using this method is exact, where the error is 0%. So you should know that if you perform the analytical integration, you can obtain the actual area under the curve. However, in some problems, your function might be complicated like this case, where you cannot perform the analytical integration to solve the problem. Numerical method is very useful to solve this kind of problem. In this method, we can approximate the area by using a rectangular bar. For example, let's have the n equal to 2 bar to represent the total area here, and you can find the step size delta x, which is also the width of the bar, equal to the upper limit b minus with the lower limit a divided by number of bar. By doing this, you can form 2 bar under the curve, and you can find the area easily by using the multiplication between the height and the step size, which can be computed by using this formula. So you just need to take the summation of the area for the first bar plus the second bar in order to approximate the actual area. However, if you look at this graph, the truncation error is too large. Since the error is too large, therefore the summation of A1 plus A2 is far away and not equal to the actual area. Therefore, we can say this numerical solution is not acceptable. Theoretically, if we can increase the number of bars to infinity, in this case, your delta x will approximate to 0. By using infinity bar under the curve, we can obtain the actual area under the curve. In this case, the actual area is computed by using the summation of all the infinity rectangular bar. If we are able to use this parameter, then we will obtain zero truncation error where the solution is exact. However, in actual, we cannot set the parameter where the delta x equal to 0 or the n equal to infinity bar. Although we cannot obtain exact solution by using numerical method, we still can obtain good approximation by reducing the truncation error. For example, if we increase the number of bars to 8 and we compute the total area under this curve by using this 8 bar, and you will see that the truncation error is much reduced. If the error is acceptable, then the area computation by using this 8 bar has good approximation to the actual area. This method is known as the numerical integration. In this problem, the velocity data is given in the continuous function. If we want to know the displacement when the time is equal to this, then we can perform the analytical integration. So we can obtain the displacement data by integrate the velocity data with respect to time. Integrate cos, you obtain sine, and then you need to divide by the pi over 4 to give you the constant 8 over pi. And don't forget your constant. If the initial condition is known, for example at t equal to 0, the displacement x is equal to 0, then we can substitute this information inside to obtain the unknown constant. Sin 0 gives you 0 and x0 is equal to 0. Therefore your c is equal to 0. And in this case, substitute back the c inside, you can obtain the displacement equal to this function. Then you can substitute the t. Let's say t equal to 2, you obtain the displacement equal to 2.55. So at t equal to 2 here, then the displacement here is equal to 2.55. By using the similar approach, you can find the displacement at t equal to 4, 6 and 8 seconds, which is equal to this answer. Then you can plot it. You can also continue to find the displacement at other times by using the same approach. This approach is known as the finite integral. Besides that, we can also use the finite integral to get the same answer. For example, to find the displacement at t equal to 2 here, then you can integrate from 0 to 2, which is from here to here, and then this area actually is your integration result to find the displacement at t equal to 2. You can repeat the same procedure to find the displacement at t equal to 4, 6, 8 by replacing the upper limit. For example, at t equal to 8, what you are doing is you integrate from 0 to 8 here. So you want to find the area under the curve, and the total area under the curve here is equal to the displacement result at t equal to 8. Both approaches give you the same answer. In simple, if you want to find the displacement from the velocity data, then you need to perform the integration. By integrate from 0 to t, for example t equal to 5 in this case. So by integrate this, you are actually looking for this area, and this area is the displacement data at t equal to 5 here. On the other hand, if you are given the displacement data, you want to find the velocity data at a particular moment, for example at t equal to 5 here. Then it's equal to find the slope at this particular moment. The velocity data can be found by using the differentiation. So once you differentiate the displacement with respect to time and substitute the t inside, for example substitute t equal to 5, then you can obtain the velocity at t equal to 5 here. Let's use the numerical integration to solve the same problem. Imagine that you want to find the displacement from the velocity data at t equal to 2. So we know that to do this, we can perform the integration on the velocity data by taking the limit 0 to t equal to 2. The velocity data at t equal to 2 here is actually the area under the curve from 0 to 2. So it can be also equal to A1. By using the numerical integration, we can approximate this area by taking the summation of numerous rectangular bars, where the s dot is the height of the bar, which can be represented by the velocity, and the delta t is the width of the bar, which can be represented by the step size of the time. If we let the parameter n equal to 10 bar, then the step size delta t will be equal to 0.2, which is equal to b minus a divided by n. b is the upper limit, which is equal to 2, a is equal to the lower limit 0, n is equal to 10. The area of this bar is equal to the width multiplied with the height. Let's approximate the area A1 by using this 10 bar. By taking the summation of area from the bar 1, bar 2 up to the bar 10, then you can find the total area, which is equal to 2.74. 2.74 is the displacement result at t equal to 2 that is approximated by using the numerical integration. Compared to the actual result that you obtained previously by using the analytical integration, this numerical solution has around 0.19 absolute error. You can repeat the same procedure to find the displacement at t equal to 4 by using this numerical method. The numerical solution is 0.4, but the actual solution is equal to 0. Therefore, you have around 0.4 absolute error. You can continue to find the displacement at T6 by using the summation of area 1 through 3. So this is the numerical integration, and to reduce this error, you can consider to further increase the number of bars or reduce the step size. Then you can obtain good approximation from the numerical integration. For the numerical integration, so far we are using the rectangular bar in order to approximate the area under the curve. For other numerical methods, we can also consider to use trapezoidal bar and more complicated geometry through the Simpson's method. You will learn all of these methods in the numerical class later. Bend your mind in this course, we will only focus the analytical differentiation or the integration. Numerical methods will not be covered in this course and is out of the scope. But at least you need to know how to differentiate between the numerical method and analytical method. You should also know the reason and situation when we will apply the analytical or numerical method. In simple, for these three problems, you need the integration of the fx and fy function. If these fx and fy functions are provided and they can be solved by using the analytical method, then we will go for this for highest accuracy. However, if the fx or fy functions are too complicated to be solved or is given in discrete form, where you can see only discrete measurement, which is given in the red point, are available. So in this case, we have to use the numerical method to solve it.